Good morning. Happy Friday. I hope your day is going well, and I hope your weekend is wonderful. Next Monday at 1:10 p.m., we will not do problem set 4 and quiz 4, but instead we'll take the first midterm exam. And the first midterm will be over chapter 7, 8, and 20. So that would be Lewis structures and Vesper for 7, organic, thanks for playing, valence bond and molecular orbital for chapter 8, and then chapter 20 would be the OChem stuff. And when you come to class next Monday, also bring the Exam Prep 1 worksheet. That's a single page, double-sided. The question's given, the answer is given. Show your work, how to go from the question to the answer. That's how to solve it. And I am hoping that this is pretty chill, but if it's not, boy, definitely reach out to me, the tutors, your friends, and stuff like that. You all need those skills before we start. You'll turn in the organic chemistry lab that we started on Monday. And also Monday after the midterm, we do have a lab. It's called the Molar Mass of a Volatile Liquid Lab. It's really cool. Make sure you have the in-class version. This is a lab where you will definitely need goggles. We are back in the lab. Everybody has to be in the lab. I've been asked that a couple times. Yeah, we're going to be back in the lab. It's kind of a fun lab. Lots of flames and boiling water and stuff like that. Should be pretty cool. And then also, like I said, next week weather might be a little funky. So just to let you know, there's an alert system that Mount Hood uses to sign up if you want immediate things. Honestly, usually KPTV and KATU and these kind of things have just as good of ways to monitor when schools are closed, but just let me, it is a possibility. If I find out anything, I will send you an email too. Always something. Any questions? Any of that? Let's start reviewing. Now, I actually had several questions about this question. At the end on Wednesday, I kind of said, oh yeah, bond order, blah, blah, blah. And I think it's worth kind of doing it again because I had more questions about it than I realized. So if you already know the answer, awesome. But I want you to find the carbon-oxygen bond order in formaldehyde. And formaldehyde is an aldehyde. It's a single carbon aldehyde, so it's got a carbon-oxygen double bond. The best way to do this would be to draw the Lewis structure, and from the Lewis structure you could find the bond order. So work on this just a little bit, and then we'll talk about it, and just make sure that everybody's up to speed. Okay, so if you want to draw a Lewis structure, you always start by counting the valence electrons. Carbon is 4, hydrogen is 1, and there's 2 of them. Oxygen 6, so 4 plus 2 plus 6 is 12 valence electrons. And if you divide it by 2, you'll see that there are 6 pairs of electrons. So the next thing, put the central atom in the middle. It's usually the first atom listed. It's never hydrogen. it's always the lowest electronegativity. And oxygen, fluorine, nitrogen, these are really high electronegativity, so definitely carbon's gonna be in the middle. And you can just put the atoms around anywhere. You want to connect those outer atoms to the inner atom with a bonding pair. So those 3 lines represent 3 pairs. I've got 3 pairs left. Put electrons on the outer atoms first, and if you have any left over, put them on the inside. So I'm going to use 1, 2, 3, my remaining 3 pairs to give oxygen an octet. Octet means 4 pairs. Each pair is 2 electrons. That's where the octet comes from. So oxygen has 1, 2, 3, 4. It's happy. Hydrogen only needs 1 to be happy. But you should definitely look at the middle atom. And in this case, you can probably see there's only 1, 2, 3 bonds, and carbon must have 4. The only ones that can go under 4 are boron, beryllium, aluminum, those kind of things. So I'm going to take one of the lone pairs, make a double bond right there. Now carbon has 1, 2, 3, 4 pairs. It's happy. Oxygen still has 1, 2, 3, 4 pairs. It has to share one of them with carbon. Everything is good. Questions on that part? Bond order is literally the number of bonds between 2 atoms, all right? So if you talked about carbon-hydrogen's bond order, you would say 1. There's a single bond, all right? And as you can tell in this structure then, the carbon-oxygen has a double bond between it. 2 bonds would be a bond order of 2, all right? So that's literally all bond order is. There is one wrinkle we'll look at in the next problem when you have something that resonates. But nothing in formaldehyde here is resonating. That's the only structure you've got. Questions on that? Yeah.
If it asks for the bond order, like the whole compound, what you do?
You will never have the bond order of a whole compound. You can have a bond order of resonating structures, all right? So for example, like benzene, which is C6H6, the carbons in the middle, you could say that those aren't doubles or singles. They're like bond orders of 1.5. But that doesn't apply to the carbon hydrogens in benzene. All right, those are all separate. You'd say those bond orders are bond order 1. So it's only specific to like 1 bond here, or if you have a resonating structure, then it might apply to the resonating atoms, but it's not for the whole molecule and stuff. Cool question. Other questions? Okay, so the one wrinkle that can happen is when you have something that resonates, all right? This is formate, and formate, punchline, it does have a molecule, it's gonna have a resonating bond. So what I would do to answer this question was the bond order. Start by drawing the Lewis structure for formate, all right? And then you want to look at the carbon-oxygen bonds. And again, because it resonates, we're going to do something a little bit different. So see if you can draw the Lewis structure for formate, and we'll talk about it here in just a little bit. Okay, so on this molecule, same idea. Start by drawing a Lewis structure for the formate ion. And again, first thing you want to do, count the valence electrons. So hydrogen is 1, carbon is 4, oxygen is 6, and there's 2 of them. And when it's -1, does that mean you add electrons or take away electrons? Add electrons, that's right. It's an extra electron on top of that. So here we have 1 plus 4, 5, plus 12, plus 1. So 12 plus 6, 18 valence electrons, or if you divide it by 2, that would be 9 pairs of electrons. Now, hydrogen is listed first. Hydrogen can be an acid, and this is a more acidic hydrogen. That's why sometimes you see it listed first. But remember, hydrogen does not go in the middle ever. All right, it's always an outside kind of chilling in the background kind of thing. So once again, carbon is going to be your middle atom. All right, so I would have carbon. I'll put the 2 oxygens and the hydrogens around. And by the way, you could put the hydrogen here and the oxygen there. It doesn't matter. Okay. Just put them around. But what you do want to do, like before, is you want to connect those outer atoms to the inner atoms. So those 3 pairs give me 6 pairs left. And like before, the outer atoms get octets, and if there's any left over, put them on the inside. So 1, 2, 3 gives that oxygen an octet. 4, 5, and 6 gives that oxygen an octet. I don't have any more pairs, so the outer atoms are happy, but you should double check on the inside. And you can probably see that like last time, this carbon is not happy. It's only got 1, 2, 3, and it wants to have 4 pairs. So from one of the oxygens, it doesn't matter which one, make a double bond like before. That will give carbon its 4 pairs of electrons, so it's got the octet. Happy? Question so far? Now, is there anything wrong if, say, O2 took the lone pair and made a double bond there instead of there? No. It does not matter energetically, which is what physical science is all about. It doesn't matter energy-wise if you made the double bond to this oxygen or to this oxygen. So what we have here is a resonating structure. And chemists use a kind of double-sided arrow like that to show what the structures look like. And so you could have a double bond O to the right oxygen, or you could have one to the top oxygen. And there's no energy difference here between these. So when you're talking about bond order for something that resonates, it's a little bit different than on the last one. You have 2 places, 2 oxygens that they can connect to. So in that case, you'll take the total number of bonds, 1, 2, 3, and you divide them by the number of places they can go. So there are 2 oxygens that it could happen. And again, notice you could use this structure or this structure. It doesn't matter. This one you'd have 1, 2, 3 bonds, and there's 2 places they can go. So the bond order here is 3 halves. It's like 1 1/2, all right? And sometimes you'll see diagrams where there's like a dot, 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 dot between the oxygens. That's not liked as much as knowing that it's resonance, but that's what it's trying to show. It's, like it says here, it's more than a single, but less than a double. All right, so it's stronger than a single, but it's longer than a double, stuff like that. Yeah, Bradley.
Could you put
Say that again, Bill.
I'm still a little lost. Like, how do you get the 3 and the 2? And they say,
Yeah. So first of all, identify if you have a resonance form, all right? And you have a choice where the double bond goes. Like you could draw it up, you could draw it to the right, all right? So when you have a choice, that's where this weird thing kicks in, all right? The top number, Bradley, is literally just the number of lines between the atoms that you're thinking about. So in this structure right here, there's one single bond and 1 + 1, 2 bonds right there. So you have 1, 2, 3 lines, 3 bonds. That's where it comes from. And those 3 bonds, Bradley, you could put them on that oxygen or that oxygen. So there's 2 places they can go. And that's where the bottom one comes from. So it's like number of bonds or lines on top divided by the number of places those bonds or lines can go. Cool question. If you had carbonate has 3 possible resonance places, all right? Like the double bond, I drew it here, but you could put it on this oxygen, or you could put it on this oxygen. So the bond order for this resonance structure, 1, 2, 3, 4 bonds, 4 lines, and there are 1, 2, 3 different places that those could go. So this one would be a 4/3 bond order. Again, most of the time bond order is pretty simple, all right? You just look at the number of lines, like this one, bond order 1. But when things resonate, that's when you get into these fractional things and stuff, so. Cool. Other questions on that? Awesome. Okay. The one place next week that you're going to need your calculator is on a problem like this. Excuse me. This is a bonds broken minus bonds formed problem. And this problem says what's basically the enthalpy for making nitrogen trifluoride. So, to solve this problem, first of all, you should draw Lewis structures of everything up there, all right? And see what kind of bonds you have. And once you do that, the bonds that you break, those are the reactant bonds. And the bonds that you form, those will be the product bonds. So when I say bonds broken minus bonds formed, it's like all the bonds on the reactant side minus all the bonds on the product side. And I will absolutely give you these kind of numbers. You don't have to memorize or put them on your cheat sheet or anything like that. But use these values. See if you can figure out, excuse me, what the enthalpy, the delta H, is for this reaction. So how much energy do you get out or do you need to put in to make nitrogen trifluoride? So see if you can do this, and we'll talk about it in a little bit. So first step, draw the Lewis structures. And some of these are pretty obvious, like N2, and there's only one N2, all right? If you had a big table of values, you might want to know if it was an N triple bond or an N single bond, that kind of thing. But for the kind of problems you're going to see, that's probably pretty obvious. But what is not always obvious is something like NF3. Because NF3, when you draw it out, you can see there's not one, not two, but actually three NF bonds, all right? And that's the part that can be kind of tricky about these. The other thing to pay attention to is that you only need half of an N2. You don't need a full N2 in this problem. So combining all that then, you've got a triple bond. Triple bond is 946, but you only need half of it. So bonds broken would be 1/2 946, and you need 3/2 of the fluorine, which is 159. This means add up all of the bonds that are being broken. So the sigma is a summation sign there, just means add up all of the bonds that are being broken. So 1/2 of 946, 1/2 of an N2, and 3/2 of the F2 bond, that would be all of the bonds that are being broken up. Now from that, we're going to subtract all of the bonds that are forming. And this is where it's kind of cool to do the Lewis structures, because when you draw NF3, there's 3 NF bonds. So we would go 3 times 272. Because 272 is just a single NF bond, and you've got 3 of them here. So through all of this in your calculator, comes out to be minus 105 kilojoules per mole. So this is an exothermic reaction. When delta H, the energy is negative, energy is released. And usually exothermic reactions are reactions that will happen. So nitrogen trifluoride should happen, no problem. If it was positive, you'd call it endothermic. Any questions on that?
What is nitrogen trifluoride?
I honestly don't know what they use it for. That's a good question. Fluorine always does wild chemistry compared to chlorine, bromine, and iodine. So like nitrogen trichloride, I know they can use as a way to get heat out of a system. Nitrogen trifluoride, honestly, I don't know, Marquis, so I'm not going to lie, man. I would go to Wikipedia and look up it.
Well, so in theory, it's the same. Like if I were to just somehow have I'm trying to. How do you join nitrogen and fluorine? They pump both of them into a glass layer and they combine.
Right on. You've brought up a really cool question, and by the end of this term, I'm going to give you a better answer.
Okay.
But, all right, but let's do a kind of a hypothetical situation, all right? Kevin's a cool guy. I like talking to Kevin, all right? So me going to Kevin and say, hey, Kevin, how you doing? What are you doing this weekend? Not a big deal, all right? So that would be exothermic for me. I like going to see him, you know. Talking to you would be endothermic. No, I'm just joking. You'd be exothermic too. But anyway, that's neither here nor there. Now, here's the thing in chemistry, though. There's always a price to pay to start the reaction, all right? And to get to Kevin, it might be an easy price. Like if I go this way, what's up, man? All right, no problem. That would be easy. And at the end, I would get that energy back and stuff. But Marquis, there's nothing that says I couldn't, you know, go, oh yeah, Kevin, yeah, and then I go this way, right? And I kind of go all over the place, and it takes me more energy to get there. I would still get to Kevin, but it's a higher energy cost initially. Now you're going to get that energy back at the end. That's what that number says. But initially, you have to put in a lot of energy. So honestly, I would guess that breaking a triple bond is pretty high energy. I would guess this would be more like my last way to get to Kevin. It would take a lot of energy. Like if you just randomly put into an F2, unless you heat it up a little bit maybe, that probably wouldn't happen. That would be my guess, Marquis. Now, I don't know for sure. This cost of starting a reaction is called the energy of activation. And that's something we'll talk about by the end of the term. And that's good. So for example, our bodies, our DNA, caffeine in my case, in my bloodstream, whatever, all these things are going to go to CO2 and water eventually. But thankfully, they have a high energy of activation. reaction. So I won't just spontaneously combust into CO2 and water because there's a really high energy of activation. It's not going to happen normally. One day, yeah, no doubt it will, but it's not going to happen right away. So why that's relevant, if you put N2 and F2 together, I haven't done enough fluorine chemistry to know, but I would guess it might be difficult, all right? So you'd have to massage it, get over that energy gap, and it would come back to you at the end, but it might be a pretty high energy gap, all right? So yeah, so when you do a reaction, there is like this overall energy change. And exothermic means you bet it wants to happen. But how high that cost is to get started, honestly, I don't know.
And I mean, this might be a question that'll be answered by the end of the term.
Right on.
As far as we've learned thus far, through 221, for all those who've taken it, the only energy that I recall being expressed is heat. Is there another energy equivalent that would, or something that would be quantitative energy or quantitative energy?
Yeah, it's sometimes in business they say you have to invest money to make money. It's the cost of doing business, and if you're a good business person, at the end you'll get it back. But it does take that initial part. So this is like the overall beginning and ending. All right, and so me here, me talking to Kevin, that's what we're looking at. But what we're going to start talking about is how much energy does it take to start the reaction. All right, and that's a little different thing. Now, why we're not talking about it initially is because you get that energy back at the end. And so this reaction, you're going to get it all back, but how much it takes to get started, I don't know. That's why generally as you heat things up, they go a little faster because you're able to overcome the energy of activation barrier to make it happen a little faster. Anyway, this is a really cool subject, and I probably shouldn't have spent so much time talking about it right now, but I love your question, man, and just realize that, yeah, that these numbers say that they're going to react, but how difficult it is to start, I don't know. Yeah, so. Questions on that? This is a little off target, sorry. Prophet back on, et cetera, et cetera. I have such things to show you. No. Anyway, all right. Here's a question, kind of like the question we had on the one quiz. It says, which of the bonds is least polar? All right. So which one is going to have the less separation of electronegativities? All right. Which one is going to be most like the which atom is going to be most like the other atom is what it's saying. It's not AC/DC. I'm sorry. It's another weird instructor thing. See if you can figure it out. I'll shut up. So returning back to what we're supposed to be talking about, this is the question that talks about the polarity of a bond. All right, so you have two random atoms, and notice that all of them have boron on one side. That'll be helpful to us. Now, the way to answer questions of polarity is to use electronegativity. And at the back of problem set 1, there was a table of actual numbers associated with electronegativity. And if you have that, you can figure out the differences in electronegativity, blah, blah, blah. But if you don't have it, which is what happens most of the time, just remember that fluorine is the most electronegative. It wants electrons more than anything else. Now, oxygen is second. It wants them a lot too. It does those out to fluorine, but it wants them a lot. Nitrogen and chlorine are next. But overall in the periodic table, electronegativity increases as you go up and to the right. So if you think about this as a periodic table, hydrogen upper left, francium is in the lower left, helium upper right, and either radon or argentium, depending on which periodic table you have. Our periodic tables are old, so radon is there, that's fine. Anyway, up and to the right. So they're going to get bigger as you go up and to the right. And this is a trend. So aluminum would have a lower electronegativity than silicon, but silicon would be less than nitrogen. But even more basic than that, the closer the atoms are together on the periodic table, the more likely they're going to be similar to each other. And you can see that boron right there is closest in that list to carbon. All right, nitrogen would be 1 step away, oxygen 2, fluorine 3, etc. So the boron-carbon bond should be less polar than the other ones, all right? Again, these 3 are some of the big ones on the periodic table for electronegativity. So that would be another way to say that probably is going to be it. But again, punchline, least polar, closer together on the periodic table. Questions? Now, you can have polar bonds, but the molecule itself may or may not be polar. So the question here is, which of the following molecules is polar? Now, most of the time you can just guess that things are polar, but one of them up there is not polar. See if you can figure out which one it is.
Which one is polar?
Sorry, yes. Thank you, Marquis. I'm glad it's Friday. Yes, let me rephrase. Sorry about that. Which molecule is polar, not which molecule is not polar. Sorry about that. So, yeah. You got it. Come on, Kathy, come on.
Teaching I have.
My bad. I'm glad it's Friday. This is the structure for carbon dioxide. Now, oxygen, one of the most electronegative atoms of all, and oxygen is going to pull on carbon really, really strong. So the carbon-oxygen bond is very polar. Oxygen pulls the electrons away from carbon. But there's a second oxygen, and that oxygen pulls in the equal but opposite direction. So the two polar parts cancel each other out. So CO2 is considered to be a symmetric molecule. The oxygen on the right and the oxygen on the left cancel each other out. So even though the CO bond is polar, CO2 itself is nonpolar. And anytime you have a central atom surrounded by all the same stuff, it's going to be a nonpolar molecule. So what I would do on this problem is I would build all of the structures except neon. All the atoms are just individual atoms. Those are going to be nonpolar. But Cl and F, only two atoms. Fluorine pulls really hard on chlorine. Chlorine's strong, but nowhere near as strong as fluorine. This one kind of has to be polar. All right, there's no way to get around it. Boron trichloride, the boron-chlorine bond, very polar, but again, everything around the boron is the same. So this would be a non-polar molecule. And nitrogen is just N pulling on N, that would be non-polar as well. Any questions on that?
You said that chlorine and fluorine would be non-symmetric, and then boron trichloride and carbon dioxide would be symmetric.
You bet. That's right. Even N2 has a symmetry if you put a line down the middle of it and stuff. You bet. This is the only one which is asymmetric. That's right. That's right. Yep. And a lone pair can break that symmetry too, by the way. So. Yeah.
Graham, I actually had, it's not really a question as much. Well, it is double bar down. So I actually did that as, I've done this before, but chlorine, or I did this carbon, iodine, and fluorine, which is still made it polar. It made it the only polar one because then obviously the iodine would make it very polar.
Yeah.
But that being said, would that be, if that was like a chlorine, if it was a ClIF, would you call that like a chlorine iodide?
If you think
That would be like a carbon iodide.
that could be a formula, this is the only way you could get a Lewis structure Marquis. And the carbon has an octet, which is happy, but a big red flag here is that fluorine doesn't make double bonds, all right, ever, because it's more into electrons than anything else. So you'd run into problems from the fluorine having a double bond. Right now, 1, 2, 3, 4, 5, 6. No, wait, something's wrong with my structure.
You have to be two more, a lone pair on the iodine.
Yeah. You're going to run into problem. Let's see. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. So yes, it would have to be that. You're right. It wouldn't work on that one. You're going to run into formal charge issues and stuff like that. So that would be one way to say, ooh, that's not CIF, it's CLF. And Marquis, some people do that. If you ever see one and you're not sure, you come to the front and ask me, man, because this is not supposed to be the trouble problem on this kind of thing. Yeah, so good. So yeah, chlorine once in a while will be in there. Carbon always wants to have usually 4 pieces around it. So with iodine, you'd see CI4 or CCl4, stuff like that. But you'd probably see more atoms around carbon if that was it. But again, if you ever have a doubt if it's Cl or Ci, man, come right to the front and I will tell you. So cool. Sorry about the confusion. Yeah. Other questions? Okay. Which one of these is most likely to have a dipole moment? Now, dipole moment is just a fancy way of saying that it's polar. A dipole is measurable polarity, and there are devices that can be used. So this question is saying, which one of the following is polar? All right? So you could draw a Lewis structure for each one, which is probably the best. It won't be E. The atoms by themselves are considered nonpolar. That being said, see if you can figure out which one of those has a dipole moment, which one is polar. This is really fast Lewis structures for all four of these, not including radon. Which one of these doesn't have the symmetry that Kevin asked about earlier?
Nitrogen.
Nitrogen trifluoride, that's right. That lone pair is enough to break the symmetry. So when you draw this out, all the rest of them have symmetric atoms around them, all right? Carbon has 4 hydrogens. It's tetrahedral, but that doesn't matter. They're all the same. Beryllium only needs 2, so it has a fluorine on each side, symmetric. Sulfur has 6, but again, everything's the same around it, no lone pairs. That's nonpolar. This is the only one that doesn't have that symmetric part to it. That lone pair breaks the symmetry. So not everything around the nitrogen is the same. That means it's going to be polar. That means it's going to have a measurable dipole moment. And you can actually put it in a machine and see how much there is and stuff like that. Questions? All right. I'm just going to go through this one fast because I don't think I'm going to be able to do them all on Monday. BCl4, when you draw it out, is a tetrahedral boron. There are 4 chlorines around it. Anytime you have tetrahedral, sp3. Okay, so we'll start. I'll show this answer on Monday, and we'll be good to go. Thank you so much for being here. Have a great weekend. I'll see you on Monday.